this?
Yes. All right, so I'm going to talk about complementarities and externalities. Well, we know that in market design, this is a corner of market design literature, which is quite challenging and difficult. And the reason is that when preferences exhibit just a very slight degree of complementarities, and suddenly we don't have stable matching in two-sided market, nor competitive equilibrium in one-sided market anymore, right? Yet we cannot really ignore these issues because these are really crucial elements of a lot of practical applications. So my talk is a little bit of a survey talk. I want to show you several works and really convey to you a relatively general method to construct approximate solutions in both one-sided and two-sided market. And the features of this method is it's not really follow the type of beautiful greedy algorithms that Al explained this morning, but rather a non-greedy approach. And let me kind of step back and explain what it is, right? So in computer science, with first type of algorithms that we learn, we call the greedy algorithm. We build the solution piece by piece, and every time we only look one step ahead, right? And it works well for several problems like minimum spanning tree, minimum base of the matroids. But unfortunately, in a broader domain or even give extra constraint for this problem, the greedy algorithm failed miserably. And then there's another technique, which I learned a lot from your approximation algorithm book, that is LP relaxation, right? So we write any optimization program as an integer program, and we relax. My variable is not 0, 1, but any variable between 0 and 1, and we solve this linear program. And if you're lucky, the solution came out to be an integer, then perfect. If not, then we're going to try several methods to kind of route this fractional solution to a nearby integer solutions. And the beauty of this approach is that it works for a much broader range of problems, but also give insight into why the structure of the problems where the greedy algorithm works. Okay, so I want to convey to you that in market design, the same insights actually hold, right? So the two beautiful building blocks, cornerstone of market design, that differ except from algorithms or Tatherman process in market design, competitive equilibrium, are actually just greedy algorithms. And it works very well when preferences are substitutes. And without these conditions, not only that this greedy algorithm stop working, we have a more serious problem that stable solutions or competitive equilibrium doesn't exist anymore. Okay? So the approach that I'm proposing is called relax and route. So first, I'm going to assume that in this market, things are divisible. And I'm come up with a fractional stable or fractional equilibrium, and I'm going to route it. Okay? So this approach turns out to be quite flexible, work well for preferences beyond substitutes, and importantly also give insight into why we have the original result when we have substitute preferences. Okay? So I'm going to give you a few example case studies of this approach. The first one is stable matching. So everybody here knows what stable matching is, but I'm going to give you an example instead of definitions. Here I have 2 hospitals and 2 doctors, and the preferences are given over here. And I have 2 possible matching. Matching number 1, the 2 both, and I denote it's 1, 0, 0, 1, and this one is 0, 1, 1, 0. Okay. So I can express this matching as a matching polytope, where each of the row of the constraints correspond to the constraint that I can sum of these 2 edges are at most 1. And each of the columns are just the variables of these edges. And I can really express an order for each of the row, mimicking the preference of these agents. Okay? So there's a concept here that a solution dominates a column. It means that there exists somewhere a constraint that is binds. And furthermore, I look at this constraint and the order preferences. This row really like every coordinate where x is positive to the column C. Okay? So in particular, this solution here, 1, 0, 0, 1, does not dominate the coordinate correspond to D1 and H2, because D1 and H2 are actually blocking this matching. Okay? So there's two constraints here that is possible to block, but both of these constraints, the matchings actually like it more than the existing positive coordinations. Okay? So a dominating solution is a solution that dominates every column. That's the definition. Okay? So Scarf lemma 67 said that give me a matrix, give me some sort of strict ordering on these columns for every row. There will be an extreme point of this polytope that dominates every column of A. Okay? This is a beautiful theorem that he came up with to prove the non-empty core of the balance game. And here, if we apply this, if P is a polytope of the bipartite graph, we know from Vijay talk that it's an integer polytope, then all the extreme points are integer. And by this theorem, the extreme point, the integer, correspond to a stable matching. Therefore, we have an alternative proof to show that there's a stable matching in bipartite graph. Okay? So why is it good? Well, it is good because we can use the same concept to extend it to matching with couples. So now here's an example of matching with couple. Couple now have preferences over pairs of hospitals. And I can construct the same matrix again. Here's a constraint for the hospital and constraints for the couples and the doctors, giving the same kind of relatively order that capturing the preferences. And I solve for the dominating solutions. Now,
sorry, when you're given a constraint for a couple,
yep.
Could you also be for that couple D1, D2? Mm-hmm. Can D1, D2 also have their own singleton constraints? So that suppose they cannot go to the same city and be happy together, mm-hmm. At least one of them is happy?
Yeah, yeah. So they can have preference over pairs of hospital and empty, yeah, and single. Okay, so now because of this preference over pairs of hospital, we don't have an integer polytope anymore. And example here, dominating solutions will be fractional. Okay, so that is kind of the relaxing part of the algorithms. So now here comes the routing part. Okay? So given a fractional dominating solutions, I'm going to route it to an integer one. And I call a routing is good. First of all, it only route the fractional variables. Okay? I don't want to route 0 to 1 or 1 to 0. And second, this routing does not violate the couple constraints. And if the couple constraint was binding, it should keep it binding. Okay? So if I have such a good routing, then and I might violate this capacity constraint at hospital. This is okay. And I call that new routed capacity C star. If X is a good routing, X star is a good routing of dominating solutions, then X star will be a stable solution with respect to the C star. Okay, so that is really the heart of this routing algorithm. Have to be quite careful in the way we route. So can we got that routing? So yes. So the property of the couple, yeah.
Look at the lemma here.
We did hand wavy, but yeah.
So n equals rounding is stable?
With respect to the new capacity C star. When I route, I get the X star, and I might have a different C here. It becomes a C star.
And you're going to limit the gap between C.
Yeah. Yeah. Okay, so now really the goal is to route in such a way that the C star is not so different from C. Okay? And yes, we can do it. The key thing is that in this constraint matrix, I look at the hospital constraints, only at most 2 number ones there. Okay? And only 1 number ones in the doctor and couple constraint for every row. And if this is a constraint matrix, I can route such as C star is at most C plus 1. So it means that I might increase every hospital by at most 1 position, and I will obtain stable. So this one weakness of this one is that it doesn't really give me other directions of the bounds. I want to bound such as C, and C is not also too kind of lower compared with a C. So here's another result. I can make a routing such that C is not more C minus C star absolute value is less than 2, equal to 2. And furthermore, the sum of C star is between sum of C and sum of C plus 4. So what does it mean? The interpretation is that we can somehow switch some of these jobs from one hospital to another so that we don't increase any hospital or decrease by more than 2. But overall, the aggregate jobs that we redistributing is not too far from the original one. So that is theorem. So the worst case bound. So we run some simulation on this data, 270 doctors, 18 hospitals, run it 200 times. And it turns out in practice, it works much better. So even if I have 90% of the doctor belong to couples, I only really violate 1 positions for each hospital. Okay. So, well, the generality of this approach is that, well, I don't really have to require that the hospital constraint have at most 2. It can have 3, 4, 5. If I have at most K, such number ones, then I can find a new C star where the violation is about K minus 1. Okay. So I'm so excited. I tell my wife, oh, I have these new algorithms that not only solve 2-body problems, but you can think about 3 or 4 bodies problems. I imagine a doctor can really invite his buddy or his roommates, join with him and his girlfriend to apply for jobs together, right? She doesn't like it, said that please don't solve that problem. So I talked with Alex, Taiwan, and he told me, here's another multi-body problem that is a little bit more important. All right, so here is stable matching for the refugee resettlement problem. I have 4 families in these pictures, and here's the size of the family. This family has 1 kid, 1 adult, and 1 elderly. And I have 3 localities, and each of these locality has a capacity of how many kids. So this should be not L1, but it's really the kid symbol. And yep.
You mentioned these interesting variants. Can you allow a negative constraint? So,
Yeah.
So you don't want your enemies to end up in the same hospital?
We can. Greg will come back to that. Okay. So a matching here would be kind of matching family to locality so that we don't kind of over capacitated these kids. Okay. So again, so in refugee resettlement, we have preferences of these families over locality, and the locality, instead of having preferences over the kid of the family, it's going to have quite fairly complex choice functions. So the choice function is really trying to maximize a weighted way of this matching that satisfied all this knapsack constraint. So it's a fairly complex integer program, and the weight for each match is really capture how likely it is that this family can find jobs in that locality. Okay, so this is a relatively non-substitute choice functions. So we are going to look at this problem and think about a concept called group stability. It really means that, given the existing matching, I cannot find a new group of families so that match it to a new family, and given this extra access, they are going to accept the F prime instead of, or together with the old family that currently matched with. And it's much stronger, that is much nicer than just a pairwise stability because of non-substitutability. So the way that we can construct this back to the scarf lemma is the following. So here again, I have the family constraints and I have the locality constraints in the same way as before. But now, remember, the locality doesn't have a strict order on the family anymore. It has a complex linear integer program. So the way we do it, we're going to make a lot of copies for each of the match. Okay? And each of the copy, we're going to label it with a set of price on kids, on adult, and on senior, so that it satisfies this inequality. So it's really kind of, I have a budget of that value and how I would like to distribute that budget across the kid, the adult, and the elderly. Okay? So it turns out that if I do this and I make the locality order preferences according to this price, and I solve the scarf lemma, and this at the dominating solutions, those prices going to give me the dual certificate to show that the choice function is actually optimal. Okay? So that is kind of very nice way that we borrow from the literature of matching with contract to solve a more complex choice function. So the theorem say that there will be a group stable where we violate this constraint by a little bit, and that little bit is measured by the sparsity of the constraint matrix, which is given here. Just like give you a rough calculations that how much is this sparsity and how much is violations. So if you think about a locality, have about 250 positions, and the family size about 8 people, then we kind of might violate it by 10%. So nice working with Alex because he has data on refugee resettlement, and we run the simulations, and it turns out it's in practice it works much better than the worst case. So max violations, especially for the kid constraints, is probably the most serious one. It's 12%, and on average is violate only 5%. So that's it. Yeah.
What's the source of sparsity in the couples problem?
The couple problem, that's only 2 positions per reference. The couple have only 2 jobs. And here's one family can have multiple kids and multiple adults. Yes?
So what happens if you blow off the quotas? So a minimum number of people in a city.
Yeah, that's the harder one. Yeah. So here are some other papers that we did in a similar way. So get back to the questions of can we handle negative? So yes, we can, but to some certain level. So the A matrix in the scarf lemma doesn't really require A to be positive. It can be negative. And so we can capture, for example, proportionality constraints. So we want to match students to schools such that a group of students have to at least say some percentage of the total student accepted. So this is the endogenous constraints instead of fixed. So the other papers recently published, we can actually make that constraint not just a linear constraint, any monotone constraint, we can also capture that as well, together with weak priority. So that is the first story about stable matching. I want to, yes?
So I've seen things like this in the context of unipartite matching, whereas the market gets large, you can violate doing a vanishing proportion of constraints. But it really, there's some assumption about, the number of the diversity of preferences growing as the number of
I see, yeah.
the individuals.
Yeah, so the beauty of this approach, we don't need that kind of assumptions. Any preference, any number of couples, any saddle, these are worst case scenarios. Okay.
Corresponds to your sparsity thing a bit, no?
Sparsity is just like the size of the family. That's based on that.
Sorry, so couples generally is NP hard, right?
Right.
So your result says some has a complexity theoretic corollary or no?
No. So it uses scarf lemma, which we don't know what PPAD are. So it's not an NP because now we allow it to relaxing. So if you ask questions that given this capacity, is there a stable matching? That's an NP hard problem. But now we allow it to relaxing, and we said there exists one. So that's not a, cannot really formulate as an NP hard problem. Okay, so case study number 2 is Varashian equilibrium for indivisible goods. So the relaxation here is we go a pseudo equilibrium, and the routing is a new geometric routing that, yeah, I'm really kind of like it very much. So the framework is that we have M goods, and each good I has supply Si. Okay? And then an agent has an utility. X is a bundle in this subset of feasible bundles. And the utility depends on which bundle I'm consuming and how much money left over for me. Okay? And I don't require quasi-linearity at all. And I assume only that this utility is going to be continuous in the money and strictly decreasing. So the choice correspondence, so this is standard. So for every P price, an agent is going to look at what are the bundles that optimize the utility. The competitive equilibriums will be a pair, a price, and bunch of bundles, such that each bundles in the choice correspondence, and I sum up all the bundles. The aggregate one will less than the capacity, and it has to be equal, mark it clear, if the price is positive. I call it an alpha approximate comparative equilibrium if this price and allocations is an equilibrium where I change the capacity by an alpha. So far, so good? Yeah. So what do we know about the existence of comparative equilibrium for discrete goods? So there's two kind of subcategories. If the quasi-linear utility, which is just value of bundles minus the money, then we know a little bit more, right? So we know that gross substitute is equivalent to single improvement to no complementarities. Then we know that equilibrium exists. So recent paper, Nguyen and Kemper, show that this notions of unimodular type for the preference in quasi-linear also guarantee the existence of equilibrium. So in non-quasi-linear, we know that the notion of substitute, but it's not in that way. It means that if I increase the price, no other goods demands go down. That also guarantees the existence of equilibrium. And recently, Bovin et al. Got the new notion called net substitute, really playing with the kind of Marshall and Hickson demands, a little bit complex. Okay. So we want to bring a little bit new insight into the literature. We define a class called delta substitute. I'm not going to tell you now in a moment. Next slide. If utility are delta substitute, then there will be 2 times delta minus 1 approximate competitive. So in particular, if I choose delta equal to 1, I'm going to have an exact competitive equilibrium. Okay? And even in that notions, we expanding the literature. So it turns out it does capture the quasi-linear case. It doesn't capture the unimodular type, but we can modify the proof to get that result as well. For non-quasi-linear, one substitute is a strict, more general than substitute. It also more general than net substitute. Now you can bring this property of single improvement and no complementarity to the non-quasi-linear as well. Okay? And in the non-quasi-linear, these concepts are not really equivalent like in the quasi-linear case. So what is delta substitute? It's very simple. So delta substitute says that if I look at all the choice correspondence of the agent, if it contains more than one bundles, it has to be the case there's two bundles that I can switch from one to another by exchange at most delta I. So the things that in X is there's at most delta stuff. Things that in Y but not in X also at most deltas. The delta in one, it means that I can exchange one exchange to get from one bundle. So substitute X by Y by exchange at most delta I. Okay, so here's two interesting subclass of delta substitute. First one would be kind of imitating the substitute in non-quasi-linear, that if I increase the price of a single good, I'm looking how many other goods I'm allowed to decrease my demand. It's at most delta others. Then if it's the case, then this is a subclass of delta plus one substitute. The second would be the delta improvement. Let's say that if I, at the price P, and consuming this X bundle, which is not optimal, then I can improve it by exchange at most delta bundle. Okay? So both of these are really strict class of delta substitute. So what is a proof idea? How do we do that? So the idea is that we look at this economy, we relax it by assuming that agents can consume lotteries. Okay? So now agents' demands are going to be sitting in the convex hues of the choice correspondence instead of the vertices of the choice correspondence. Okay? So now, with that, it really shows the discontinuity of the discrete good. I can get that pseudo equilibrium, but now it's sitting right in the middle of this polytope. Okay? So what I really want to do is to round this yellow point into the vertices of this polytope. Okay? And I round it so that I get an S prime. If S prime are not too far from S, then I really get a very good approximate competitive equilibrium. Make sense?
Sorry, wait, what's that polytope?
So the polytope at the price P, each node of the polytope, each vertex is in the choice correspondent. But now I'm allowing to consume any fractional allocation inside that polytope. So now I'm rounded to a vertex, that it means that it's in the choice correspondent.
But in this fractional solution, the demand supply
Yeah.
satisfied exactly. It's not.
Yes.
So that's a bit reminiscent of what general equilibrium theories do with the Shapley-Folkman.
Exactly. Yeah. So a little bit different here that the way we measure the distance in Shapley-Folkman setting.
But Shapley-Folkman, we don't authorize ourselves in the case when delta is larger than 1 to increase the resources of the equilibrium.
Right. Yeah, I will come back to that. So here is, so two ideas, right? So it's that if my utility is delta substitute, then this convex hue of the choice correspondent has a very nice property. In particular, if I look at the edges of this polytope, it's quite short. It contains at most delta number ones and at most delta minus one. This really corresponds to the way I define the delta substitute. I can exchange one to another by sweeping at most delta goods. Okay? And here's the lemma that I'm quite proud of. If every polytope satisfies that property, like with delta uniform, then you can round it so that the maximum of every good that I violate is at most 2 delta minus 1. Okay, so this is a scale-free file. It doesn't depend on the dimension, just depend on the structure of this polytope, which is different from Shapley-Folkman theorem.
Right. So Shapley-Folkman star is non-constructive. So I'm wondering, so you don't know how to round, and rounding in general can be hard, right? So how about this one? So
This is an easy. Yeah, this is Yep.
Can you say a little bit about how exactly you do the round?
Yeah, so it's based on geometry and linear algebra. So every time, basically, you look at the Minkowski sum of this polytope, and you look at the minimum phase that contain your solutions. Okay? And by clever calculation, you said that, because it's in minimum phase, you can find a constraint somewhere on the resource constraint that you can drop it out without violating that constraint. Now, you drop a constraint out, you can lower the dimensions of the minimum phase. You continue doing that, you're going to get to a vertex of that neutral space. It's a kind of iterative routing, but based on geometry. Okay. Good. Case number 2, pseudo-market implementations. So here we have a different environment when we have no money, like the previous case. The utility are cardinal, and agents can consume lotteries, and they're going to take the expectations of that lot. Okay. So again, I have M good, agent has budget now, and utility for bundle is UJX, and for lottery, tilde is a lottery. It's just the expectations of that lottery. Okay. So the random demand, or random choice correspondent, if I give you a price P over the items and a budget BJ, you're going to go around and find what are the optimal lotteries that are consuming to maximize my expectations with the constraint that my expected budget is satisfied. Okay. So competitive equilibrium over the lottery shares are exactly this, right? A price and bunch of lotteries satisfying that each of the lottery is optimal for every agent, and I sum up the expectation of the lottery, it has to satisfy the capacity constraint. And it's going to be equal if the price is positive. Make sense? So now I have a competitive equilibrium over the lotteries. I need to implement it somehow. The implementation is say that this can be implementable if I can give you a lottery over feasible allocation, like every agent get the optimal bundle, optimal lottery. Okay? So this is really just generalization from framework of Highland and Zeckhauser for unit demand, right? So in Highland and Zeckhauser, if agents are consuming single item, then we know that equilibrium exists and it can be implemented because Volkov von Neumann theorem. Okay. So when agents consume a bundle, then we still have the first part, but not the second part. Okay. Let me show you an example. So somehow we end up with a competitive equilibrium over the lottery share, where I consume the bundle of the car and the tool with half probability. My Y consume the car and the key with half probability, and my kid consume the key and the tool with half probability. And I cannot really implement this. Right? Look, one way I can implement it is half of the time I get the car and the tool, my Y get the key. Half of the time the kid get the key and the tool, and my Y get the car. She's not going to be happy, right? So another option is I'm getting the car and the tool, the kids get the key. My wife going to get the car and the key, and the kids get the tool. Maybe reasonable, but I really have to convince my kid that his utilities are additive, which might involve a lot of tears. Right, so implementations here in this example is not possible unless we assume some structure about the utility functions, in particular additive in this case. Okay? So theorem, Gu, Bess, and Dozer, Zhang prove that if these valuations are substitutes, then you can do it. Yeah. So the proof is quite complex. It's shown by a limit of sequence of equilibrium in a setting with money, and it converge more to a setting when there's no money. So Rakesh and I, 2001, proved that actually, if the valuations are delta substitutes, then any competitive equilibrium over the outcome, you can implement it over with the violations of 2 delta minus 1. So the difference here is that any, and also general to delta substitute. Okay. And it's really based on the relax and row approach here, right? We relax to competitive equilibrium over lottery. And why is it routing? When we thinking about the implementations, because the routings actually give you the implementation. think about it, right? So we have a fractional solutions. Somewhere here. And if it is possible that we route it to integer in every directions, right? I take that direction and I route it to this guy. And I take that direction and I route it to this guy. That direction to this guy. Then the fractional solution is inside the convex hull of all these integer polynomials. And that gives me exactly the implementations of that fractional solution. So it's really kind of based on the routing in several directions that give me the implementation. So Alex and I talked a little bit about this proof. And it turns out that we can really cut the essential and boil down to why does this work for the implementations. And it turns out that it's worked very general. Yeah. So you can define a class of valuations that is invariant. If V in the class, I can add up any linear function to it, it's still in that class. So the theorem says that competitive equilibrium in the economy with money, quasi-linear, exists if and only if any equilibrium in this no money of the probability share can be implemented. So here, kind of the implications, right? So we know that now the equilibrium in the theorem Shapley-Shoemaker talk about is actually equivalent to Highland and Stockhausen. Okay. Now we can say that the Crawford and Crow are actually equivalent to the Bootish as a result of implement random bundles. And we can obtain several other new results as well. I have, was that 5 minutes, 10 minutes? So moreover, there's kind of the maximum domain that can carry over because of this equivalence. So there's this kind of maximum domain that say substitute is the largest class over certain conditions that guarantee the equilibrium exists in the quasi-linear case. So we can import that into the implementable result as well. Very good. So the key element of the proof is actually quite simple. So I look at the random choice, which is really characterized. What are the optimal lotteries that I can consume? Okay, I write out that's a linear program, and there's a doer of that program. I put that into the other side of the kind of like a Lagrange multiplier, and it turns out that actually that really the same as the lottery over deterministic choice of some new functions. Okay, so that really helped me characterize moving from one economy to the other. Okay, so that kind of really duality results come into place. Okay. Case number 4, approximate option with budget constraints. Okay, so in this model, I am having a utility which is quasi-linear, and on top of that, I have a budget constraints. Okay, and I'm consuming deterministic bundle. Okay. So without this budget constraint, it's easy, right? We know that this is just quasi-linear. If V is substitute, then we have a competitive equilibrium. Now we put a budget constraint, everything is gone. We don't have competitive equilibrium anymore. But we can define some level of approximate competitive equilibrium. I call it alpha beta approximate equilibrium. If I can change the capacity to S prime, the budget to B prime, such that the absolute value of each is at most alpha and beta. And under this new capacity, new budget, I have a competitive equilibrium. Make sense? So the theorem said that if this valuation is a substitute valuation, then we can find a price and some bundles that it satisfies this little bit complex form of approximate equilibrium. Okay. So what does it mean? Just plug it in for t. So if I choose t equal to a little bit more than 2, then I have 1 times 6 max of the PJ competitive equilibrium. It means that I can violate the capacity by 1 and the budget by 6 times the maximum price. You don't like that 6 is too much. You can go lower. You can go to T equal to 1. Then I can violate by 2 and 4 times the P max. Okay? So the T here really plays as a role to trade off between how much do we want to relax the capacity versus how much we want to relax the budget constraint. So just the idea of the proof, again, relax and route. Okay? How do we relax? We relax from a deterministic choice functions to random. Right? I want to consume a lottery that maximize my utility, but now constraint is that expected budget is less than VJ. For this random, I can have a competitive equilibrium again, and I'm going to use doer to convert that random to a deterministic bundle like before. Now, because of this, I have a very nice structure characterization of that polytope. I can use geometrically route with respect to an additional budget constraint to get that. Again, I'm not going to detail into much of the proof, but hopefully you get roughly the idea that relax and route is such a versatile kind of framework that you can apply to a lot of settings. So the advantage is that it's really good. It gives me at least, if you like, it's really a good approximations benchmark, and it really helps when we don't really have an exact solution. Right? And in practice, the additive approximations are quite small. Well, the drawback is that it's not really incentive compatible compared with all the greedy algorithms that we fell in love with, but it's unavoidable basically because you move to a complementary setting, there's an impossibility result that you cannot get all these properties. The other drawback is that we really require fixed point computations, but in our experience, we implement it is quite fast and quite reasonable. So a lot of problems that I'm currently working on, think about roommate, correlation formations, all that exchange economy, you can apply the kind of the same tool there. Thinking about different approximations as well. So here are the kind of the list of the papers that I talk in this lectures. So almost all of them are on my website, except the last one we're still writing. But I'm happy to take any questions.
So here on the last one, where you have budgets, you said, well, it depends on substitutes. What is your hope to go beyond substitutes?
Oh, so you can have delta substitutes as well.
Well, maybe we should give a round of applause.
Yeah.